This is chapter 3, section 3.4, argument with quantified statements. So we're going to explore an argument that involve the quantified statement we learned in previous sections. Here's a quick example. All computer science majors take discrete math before graduations. That's a major premise. And the minor premise is Anna is a computer science major. Therefore, Anna takes discrete math before graduations. Is that argument valid or invalid? I think you can see clearly this is a valid argument. Everyone who major in computer science must take discrete math. And Anna is computer science major, so she has to take it. Okay, so this is maybe a common sense, but this is just a formal statement where you have a statement that is true for all x, right? X in this case means all students major in computer science. And because it's true for all, then it has to be true for a specific element, or Anna in this case. And this is what we call the rule of universal instantiation. Okay, the rule of universal instantiations. So this one just saying if you have the property that's true for everything in the set, then it is true of any particular thing in that set. So the use of the word universal instantiations indicates that the true property in a particular case follow as a special instance of this more general or universal truth. I think it's quite common sense to all of you. Here is also a quick example to illustrate that. All birds, if you look at all birds can fly. Okay, this is the major premise, and then the minor premise says the falcon is a bird. Therefore, falcon can fly. Right, so this is the rule of universal instantiations, right? So all birds can fly, and falcon is a bird, so falcon can fly. Just want to have a note on the sides. When we have the valid arguments, it means if the premises are true, then the conclusion must be true. Okay, then it's valid. So this is a valid argument. However, the conclusion here, it might be false if the premises is false. So if you know about birds, this statement he say all birds can fly, this is a false statement. Actually, ostrich doesn't fly, penguin doesn't fly. So in fact, if you're trying to prove it, you say, okay, this is a false statement because there exists a bird that cannot fly, so ostrich or the penguin. But regardless, this is still a valid argument because the two premises, if they are true, the conclusion must be true. Now, the example we just went over is, in fact, a general form of the modus ponens, or we call the universal modus ponens. So when it says all birds can fly, so that could be written as the conditional statement for every x. If x is a bird, then x can fly. Right, so you can rewrite that in conditional statements. And the second premise is a falcon is a bird, therefore falcon can fly. So this is what you see, this is what we learn. If P then Q, and if given P, therefore it's Q. Now the difference here is Our statement here is claim for all x instead of just one particular scenario or case. So this is called a universal modus ponens. So informally, if x makes p of x true, then x makes q of x true. So for any x, if you can find element A that makes p of x true, then A will make q of x true. Okay. Here's another example. Let's rewrite the following argument using quantifier variables in predicate symbols. Here I have two premises. The square of an even integer is even. 123,456 is an even integer. So what do we conclude? We conclude that 123,456 square. Okay, we have a huge number. I don't know what that is, but that has to be even. Okay. Now, in this statement, the square of an even integer, that means an arbitrary even integer. And so that just means if you're going to rewrite it in the quantifiers for every x, okay, and the x values, and x is an integer, okay, then you square it, so the x squared is also an even integer. So here, this should be rewritten as follows. The major premise is written as for every x. If x is an even integer, then x squared is also even, right? So that is your major premise. If I let e of x to mean x is an even integer, and s of x to mean x squared is even, in 123,456, right, if I use that, okay, so it's just a particular values, a particular integer in this case, then the argument could be written as more symbolically or formally as if for every x, if e of x, then s of x. Now, e of 123,456, so that just means 123,456 is an even integer. Therefore, s of, you plug 123,456 into this statement, right? So that means that square is an even. So this is just a compact, formal way of writing the argument. So this argument is in fact has the form we call the universal, right? Universal modus ponens, and therefore is valid. Now, the second type of rule, let's recall the modus tollens this time. Okay, ponens. This one is tollens. So the universal modus tollens is just the same as the modus tollens that we have, but now we claim for all x values. Okay, that's why we call it universal. And we use that a lot. It's really the heart of the proof of contradiction. Okay, it's very important methods in mathematical arguments. And this one says, for every x, if p of x, then q of x. The second premise, not the case q of a. For any particular a, then you can claim it's not p of a. Okay, so basically that one is just the contrapositive case, right? If p then q, and then we have not q, therefore it's not p. Again, the difference is we have the major premises claim for all x, but then the conclusion is only claimed for one instant values. Okay, so let's look at the argument here using quantifier, variable, and predicate symbols. All computer science majors take discrete math before graduation. Now, Troy did not take discrete math before graduation. Therefore, Troy is not a computer science major. Right? If you look at this, it's actually, again, it makes sense. This is how we reason. If he graduated without taking the discrete math, then he must not be a computer science major. And you can see that is followed for the form that we have, the universal modus tollens. So the first premise, again, you're going to rewrite that as a conditional. If variable x is a computer science major, then x take discrete math before graduation. So you're going to put it formally for every x. If x is computer science major, then x takes discrete math before graduation. So to make it shorter, I'm going to let P of x to mean x a computer science major, Q of x to mean x takes discrete math before the graduation. And let's say T stands for Troy, okay, that particular one student. Then the argument becomes, for every x, if P of x, then Q of x. Now remember, x could be anyone. But here I put in T, that means for Troy. So that means if Troy did not take discrete math, therefore Troy is not a computer science major. Right? You can plug in anyone else, so that could be true for Tom, John, whatever, whoever, right? But you plug in and it should satisfy. So this form is a modus tollens, okay, and this therefore it's a valid argument. Now, sometimes we use a way to determine the validity of the arguments by use of Venn diagram. Now, Venn diagram is particularly helpful, in particularly if you want to prove it's invalid. So the way it works is we're going to draw a circle to represent how our sets related to each other's. So here's an example I say, right? So the premise is all computer science majors must take discrete math. So you're going to draw the discrete math circle that is bigger. The computer science major is smaller, okay, inside. So you see that if you pick a point in the computer science major circle, it's also automatically in the point of the discrete math circle. So that will basically represent the same meaning. If someone is in computer science major circle, then that person or that dot is inside discrete math, so therefore must take discrete math. And then you have Anna. Anna just okay, one person or someone. Okay, so let's say if Anna is a computer science major, so then I put Anna inside of computer science major. You see that then Anna is also inside the discrete math, so that tells me that Anna must also take the discrete math. Okay, so that way it's just a way to visualize the relationship between computer science majors, people, discrete math, people take discrete math, and then the particular person, Anna. So the process for using a Venn diagram to determine the validity is the following. We do it in 3 steps. You're going to draw the Venn diagram for each premise. Okay. Now, one thing to keep in mind that if we have the statement all A are B, right? All computer science must take discrete math. Then that means A is a subset of B. So in other words, the circle contained in the A circle has to be inside the B circle. In step 2, you make sure to distinguish between sets. Okay, lots of things have a certain property, an element or specific thing with the property. So computer science student, right? So this is a set. A student who take discrete math, so it's set B. So that's also a set. In the element, Anna, John, some particular person. So that will be a particular element. And the third step, you're going to see if it's possible for the premise to be true and the conclusion to be false. So you're going to try to find out, you're going to pick some element, okay, you pick some choice. If you pick that, let's say if you know X is not in set A, then X might be in set B, or it might not be in B. So you can use some choices and choose some element to see in A or B to see if we end up with um, a true premise but a false conclusion. If we can do that, then it's invalid. But if you can't find such instance, then it is a valid argument. Here's a quick example of how we use it. All integers are rational numbers. Square root of 2 is not rational. Therefore, square root of 2 is not integer. So how do we know this is a valid? Right. So I'm going to draw a diagram with the two premises here. Okay. Now recall the rational number Q is a set rational number, and Z we could say that's a set of integers. All integers are rational numbers. Okay, so all are, that means the integer set has to be a circle inside the rational circle. So I have the Z circle here, Q circle there, right? So Z and Q. Okay, that's what they mean there. Then I have square root of 2. I put the square root of 2 where is square root of 2. Square root of 2 is not rational. So that means it's not inside the Q circle. So I have to put it outside. Now look, it's outside. Conclusion, square root 2 is not integer. So is this one inside the Z? Is it possible? No, right? It's not. Because it's outside the Q circle, it must be outside the Z circle, and therefore this is impossible to find a false conclusion, and therefore this one is a valid argument. Here are the couple of common statements that we can use Venn diagram to represent. If we have the statement that says all A are B, so that means everything in A has to be in B, right? So with that statement, then we're gonna draw the circle with B is inside the circle with A. Right, so this way we guarantee that anything in B will also in A in this scenario, right, or B and A. If we have some A or B, okay, if some A or B, then that means A and B have something in common, but then there are things that in A but not in B. So this is the case where you're going to draw A and B that has some intersections here, right? So some A and B. So this is also the same as saying there exists an A that is in B. And the last scenario is if you have no A and B, no A or B, then that means A has to be separate, like outside of B, they don't have anything in common. Okay, so that is a visual way to represent these common statements, and we can use that to help prove some argument whether it's valid or not. Let's take a look at these two examples and determine whether these are the valid argument. The first one says every Linfield student live on campus. Okay, live on campus. Now we need to interpret that statement as all, right? Every means all. All Linfield students live on campus. So we should have two things or two variables here. Linfield students and student live on campus. Okay, so the big circle. Okay, so I have the circle here represent. Just say C represent all student live on campus. Then I have Linfield students. So Linfield student is a small circle inside, completely inside this time, because this represents all the Linfield students. Let's see if students inside of the L, it has to be inside the C. So that represents all Linfield students live on campus. Now, the second statement says, Freya live on campus. Right, Freya can live on campus. Now, this statement is just saying Freya live on campus. So that means Freya is just a element in the set C. Okay, so in the set C, so where is Freya? Freya, it could be here, right? It could be here, or it could be L inside the L, but it doesn't guarantee, right? It could be anywhere. But the conclusion is Freya is the Linfield student. Well, that is not the case, right? If you're looking at, it's not always true. If you're looking at the example I put here, so let's say Freya is here, right? Then Freya lives on campus, but Freya is not inside the L circle, so Freya may not be a Linfield student. So therefore, we have this is an invalid. Okay, so this is an invalid argument. You see that is using the Venn diagram, so we can see that it's not true. Now, example B, every polynomial functions is differential, right? So every polynomial functions is differentiable. So how do you draw? Again, you're gonna have two circles. You have a two circle, but every time you have every, that means all, right? All polynomial functions are the differentiable functions. So you need to have a two circle, one inside of the other. Okay, so you're gonna have a big circle. This circle is the differentiable. Okay, these are D. Okay, D for differentiable. Then our polynomial functions. So you have a polynomial function inside that is P. So you see that our polynomial functions is differentiable. Now f of x equals f of x is not a polynomial function, not a polynomial functions. So that means absolute of x, this function of x, where does it lie? Well, it's not inside of the P, right? Not inside the P. That means where does it lie? Well, it could be out here, right? The f of x could be here, or it could be there, right? So it could be in two different places. Okay, so the conclusion is f of x equal epsilon is not differentiable. If it's out here, then it's not differentiable, but it could be in here, right? So that means f of x could be differentiable, or it could be non-differentiable. Okay, so either way, correct? So therefore, this argument is also invalid. Okay, so the answer is still invalid for both cases. So see that this is very strong way or easy visual way to figure out if the argument is valid or not. All right. So okay, here's are two examples of determining whether the argument is valid or not. Now in A we have the statement say for every x, if x study, then x will do well on the exam. Then if x does well on the exam, then x get an A in discrete math. Right, so we have, so technically if you're using transitive property, you should claim that Gauss studies, right, it's into the set, then Gauss will get an A in discrete math. So that should be a valid argument. But here I'm going to show you a Venn diagram that help you determine the validity instead of using the rule. So we have for every x, so that means all x studies, then x will do well. So you need to have three circles in this case, right? So let's say one for S. Okay, the purple one, say this is study. Okay, that means it's 30 there, S. And then we also have do well. Okay, do well is the green. Do an exam, so that is the green circle. Now notice that the S inside the green or the W, because if it is well, and then it's do well on the exam. And then if X does well on the exam, then X will get an A, right, on the discrete math. So I'm going to draw the A is the bigger circle outside, and that is, I'll call the circle A. Right, the circle A here. Okay, so S inside W, W inside A. In Gauss studies, right? So where does Gauss? So Gauss study, that means Gauss is in the circle right here. This is where Gauss is at. Now notice that if Gauss in that circle, right, study circle, then Gauss will inside of the A circle represent that they get an A discrete math. So that is a valid argument. Okay, so that is that one. Now the part B we have for every x, if x study, then x will do well, the same thing, right? Then if x does well in the exam, then x will get an A discrete math. Therefore, Newton will get an A in discrete math. So here, this sentence, well, I think with the first two it's the same, but then the next two, I mean the last one, the Newton, will get a discrete math. So this doesn't make sense. Okay, quick questions as a check to understand if you understand the arguments. Check to see if this argument is valid. All zebra have stripes. Rex has stripes, so Rex is a zebra. So again, one way to do is you're going to draw the circle. All zebra have stripe, then you should have the stripe circle S, and we have a zebra circle, so that is Z. So Z is inside of S. That represents the first major premise. Rex has stripes. So Rex has stripes this time. It's inside of the S circle. It doesn't have to be in the Z circle. So if Rex is outside of the Z and it's right here, then you can see Rex is not in the Z circle. It's not zebra. So that is an invalid argument. Here's the second question. All zebra have stripes? All zebra animals. Rex has stripes. Therefore, Rex is an animal. Again, using Venn diagram probably is a better way to, or easiest way to see. All zebra have stripes, the same thing. You have a two circle, and this is a zebra circle, and you have the striped circle as here, right? Then we also have all zebras are animals, so we have another animals circle. Now notice animal circles, all we know is the Z circle has to be inside the animal circle, but how that related to S, well, we don't know, but we just draw a random arbitrary. So let's say I have the circle here must contain the zebra, right? Contain the zebra, right? So this is where the animal, okay? All zebra are animal. Now, then we have Rex have stripes. So that means it's inside, Rex is inside of the S circle. S inside of the circle. Now, then we conclude Rex is an animal. That means Rex is also inside of an A circle. So is it always true that if the Rex inside the S circle, then it has inside the A circle? Well, the answer is no, right? Because for the circle that I draw, you can see this is the place. Here's the place here, right there. So this is where the Rex could be. And you see if Rex is here. If it's here, Rex, and you can see Rex could be inside of an S circle, but it's still outside animal circle. So Rex might not be an animal. So this is an invalid argument. Right, so here's some more example question 3, and you can either use the Venn diagram to determine whether it's valid, or you use the rule that we know, universal instantiations, and modus ponens, and modus tollens. Okay, so to determine the validities of these arguments, and yes, that's for you to practice.